We're live. Hi, everyone. So welcome. I'm Mark Rowley for the University of Waterloo in the Electrical Engineering and Electrical and Computer Engineering Department. Welcome to the second during COVID Waterloo AI seminar. Today we're very happy to have Professor Matt Taylor from the University of Alberta, who is going to be talking about reinforcement learning in the real world and how to cheat and still feel good about it. Professor Taylor did his PhD at U of T Austin, and he's a fellow and member at the Alberta Machine Intelligence Institute. As well as head of a lot of other things, including corporate and academic kind of crossovers. And he's a great force in the reinforcement learning community and always entertaining talks. So happy to hear what he's going to tell us about. And I'll pass it over to Matt. I guess his one thing he added was that he's happy to take questions in the middle of his talk. So we'll be watching the Q&A section. If you're watching, you can ask a question. It'll be a bit moderated, but you'll be able to see those and ask them as you go, and that'll be fun. So. Over to you, Matt.
Awesome. Thank you, Mark. It's great to actually visit Waterloo for the first time, kind of.
Isn't the weather wonderful?
Oh, it's beautiful. Yeah, so I really do encourage you to ask questions because that way it's not just me talking at the camera. That gets old real quick. So please do drop questions into the chat. I'm happy to interact at any point. And if it's... and I will either try to address all the questions as they're asked or work them into the talk later. So with that, as Mark said, I've been doing reinforcement learning for a while. I came to Edmonton just a few years ago for the United States, and I've worked at both companies and universities. I'm really interested in getting AI into the real world. Right now, I run the IRL lab, and I do work with Amy. I'll also point out that I have active collaborations with other Waterloo folk. So I do know you guys are doing some awesome stuff too. I wanted to have one slide about Amy because not everyone has heard of it. It's one of the pan-Canadian AI centers. It was founded back in 2002, but there's been a number of successes over time. So for instance, solving checkers, launching the arcade learning environment, which is now one of the standard benchmarks in reinforcement learning. We had our DeepMind lab open in 2017 in Edmonton, and now we've got over 20 fellows as well as active researchers at the Amy not-for-profit. So I get to work at Amy one day a week, and I get to try to bring AI into the real world by working with mostly Canadian companies, but also companies around the world. I'll also give a quick shout out to my department, Computing Science. We've got around 50 tenure track faculty, and RLAI, the Reinforcement Learning AI group, has 11 associated faculty. So, and here's an example of some of our graduate classes in reinforcement learning. If you are interested in reinforcement learning, I can say it's one of the best places in the world if you are interested in applying. Of course, we do things other than RL, but that's what I'm going to be talking about today. So this talk really kind of has two main parts. The first part is kind of level setting, making sure we're all kind of on the same page in terms of what reinforcement learning is, why it's useful, and how you might be able to find good reinforcement learning problems in your research. And then I'll get more into the more technical content, talking about some of contemporary RL research, and finish with future directions and resources if you want to learn more. So if you are already an RL expert, then you can probably pay half attention during this section, and I will be sure to try to bring you back in when we switch gears. So as most of you already know, machine learning has been around a long time. You know, AI has been around since the 50s or so. Machine learning started gaining popularity in the 80s, and now it's dominant. Most recently, we've been using lots of deep artificial neural networks. But one thing we often hear from students is they think, oh, AI is deep learning. Well, it's a little more nuanced than that deep learning can be used for machine learning, and I think of machine learning as a type of AI. Since I'm in Alberta, I have to point out that lots of people are saying now that data is the new oil. which is good since the oil prices are not very good these days. But there are three flavors of machine learning. So there's supervised learning, where you're trying to figure out what are positive and negative examples, or maybe you're trying to predict, given some input, what's the output. There's unsupervised learning, where you're doing things like anomaly detection or clustering. And then there's reinforcement learning. And this paradigm is different because you have an agent that's interacting with an environment. So to my mind, this is much more of a AI-centric paradigm as opposed to machine learning, because you really have to think about something, either a physical or virtual thing that's acting, and it's really making changes. So the main difference in reinforcement learning from these other types of machine learning is that it's never told whether it's right or wrong. So let's think about an agent that is playing chess. It sees the state of the board, it takes an action, the opponent takes an action, and then gets a new state of the board. The agent isn't told that was the right or the wrong move. Instead, at the very end of the game, it might be told whether it wins or not. So instead of being told this is the solution, the agent has to interact with the environment and figure out what a good solution is. So instead of having some fixed data set that you interact with, instead, the agent interacts with an environment, and there could be some cost associated with that. So for instance, if you are a robot interacting with an environment, you have to change your batteries, your actuators wear down. Or if you are, say, making trades in the stock market, those trades could have real world impacts in terms of money. One of the things the agent needs to think about is exploring versus exploiting. That's one of the key phrases or challenges in reinforcement learning. Do I try to do what I think is best, or do I want to try something new? Because, I'm driving to work the same way each time, and then maybe one day I want to try this different road and see if it's faster. Or maybe there's a new setting. I'm driving to work each day, and today it's the first time of the year it's snowing. So maybe I want to try something different because of this new setting. So we're trading off exploring and exploiting. But there's a few different things that I wanted to disentangle. When the agent is doing this, it could be you might want to do this because of automation, right? So you have a process that a person has been doing, or a program has been doing, and you want to just automate it and just learn on its own and do better. And that comes to the improvement. You may have some existing automated process, but you want to make it better. But you could also do completely novel things. So at the very far end of novelty, you could think of, I'm going to take a robot, not tell it anything, but throw it into the world and let it learn like a small child might learn. It has to learn from its sensory motor interaction with the world, figure out what vision is, figure out how it could move around, and possibly figure out what it wants to do. So you can have a range of applications of RL where it's very constrained and you're trying to just improve something or automate something, all the way up to I want to enable general learning, and going all the way up to AGI, so artificial general intelligence, which may or may not be science fiction, but where you can think of having a program or agent which is able to perform lots of different tasks at superhuman performance. If you go and talk to companies, you can find lots of great examples of supervised learning and unsupervised learning revolutionizing their processes. Again, improving, but also enabling completely new behaviors. However, in RL, we don't see quite as much of that. So for instance, some of the big successes in reinforcement learning that you might have heard of are things like OpenAI 5 and AlphaStar. And then a few years ago now, when DeepMind beat Lee Sedol at Go. So these were really significant, really interesting, successes. But when people think of reinforcement learning now, they often think of, oh, it's that thing for video games. And it turns out reinforcement learning is actually useful for more things. So for instance, it's been used in finance. It's been used for optimizing energy, which I'll give one example of that in a little bit. You can also think of AI being used as part of other computing science or computer science approaches. So for instance, it's been used in robotics and computer vision and NLP. So reinforcement learning is a component that you could use in other, RL is a component that you can use even if your goal is not to do novel RL research. So the main outcome I'd like for this brief section of the talk is to try to give you a sense of, if you are not an RL expert, where RL might be useful for you. And my premise is that RL is a mature technology. It is ready to have lots of success outside of video games. And as an academic, I want to help enable that transformation, that getting it into the hands of people who can make these real world contributions. And part of that is getting more people to understand where RL might be useful. Because if you can identify, oh, this is a sequential decision problem, maybe RL is the right tool, then you can go and find out more, you can learn more about it, you can connect with an RL expert, so that we can help bring this technology into more applications in the real world. Okay, so what are some goals of reinforcement learning? Well, one thing you could think of doing is trying to maximize the final performance. So maybe you don't really care about how fast you learn, data is cheap, you just care about how well you do at the end. You could also think about, data is expensive, man. I want to learn as fast as possible. So you might care about your initial performance. You also might think of, well, programming is hard. I don't want to write a robot controller. I just want the thing to learn. In which case, you could try to reduce human effort. One thing that's really cool when it happens is that RL might be able to discover novel solutions. So come up with a way of solving a problem that you had not thought of. And when that happens, it's pretty cool. The last thing I'll mention is it can also handle non-stationary environments. So for instance, if you have a Mars rover and all of a sudden one of those wheels starts clogging up, you could potentially let RL help the Mars rover to learn how to compensate for that gummed up wheel. And one of the questions was, how can we think about continuous spaces and make them more robust? So that's a great question. I will put that off for now, but I will come back to that. So please do keep coming with questions. So let me just give one basic setting. So we've got Wally here, who's in a discrete grid world, and there's two places he could end up. After he gets to either the +1 or the -1, he resets to the lower left. So in this case, there are 12 places our agent could be. The actions are the 4 cardinal directions. There is a transition function. So the transition function says, if you are in a state and took an action, what state do you end up in next? So in this case, Wally can't move through walls, but there's a small chance of slipping to the side. So if Wally tries to go up, there's a small chance he'll slip and go to the right. The reward function is Wally's trying to get to that +1, and there's a small step penalty. So we can think about a policy as how do we learn or specify what action to take in which state. Okay, so let's look at some of the kind of optimal policies that you could learn. So here, it's basically what you'd expect. You go in the direction, going up around the top. Oops, wrong monitor. Going up around the top to get to the +1. Down here, you go around the bottom because you don't want to slip and get into that -1. More interesting is if the step penalty is very small. For instance, down here, you go down and eventually you will slip and go to this next state. Because if you are in the lower right and try to move left, there's a small probability that you would slip and go up. Similarly, if I'm to the right of the wall, I do not tell the agent to go up because there's a small probability I would slip to the right and get that -1. On the other hand, you could have a large step penalty where, for instance, I'm pretty close to the goal, but man, I'm just going to the right because every step, every time I take an action, I get a -2 and I just want the pain to end. And if you're in grad school, I'm sure you've had situations like that. But the point of this is that slightly different reward functions can get different behaviors. So when we're thinking about how do we define a reward function to elicit the behavior we want, small changes to the reward function can be problematic, and you need to think carefully about that. Great, we just got another question. How do you define an environment as non-stationary? Perfect, because I skipped right over that. So for instance, in this case, I'm assuming that this grid world always stays the same. But for instance, if the environment could change over the time, you might find all of a sudden, so in the lower left here, all of a sudden now there's a new wall. And you could recognize that and say, oh, something's changed, I better relearn. Or you could just implicitly learn that, oh, going right is not working, it's not working, and then over time, your policy will adapt so that you avoid that wall. So in general, real-world problems will have some non-stationarity. And depending on the situation, you can let the agent handle it itself, or you could have a person step in and say, oh, something's really wrong here. I'm going to stop, pause things. We need to take a step back and figure out how to fix this. Then there's another question about using RL to find novel solutions that we can copy and use as humans. I love that idea. So if an RL agent could find a novel solution, why not try to use that to teach people? And that's something I'll get back to at the very end, thinking about how we might be able to extract knowledge from RL agents and bring it into people. Okay, so now we've had a brief introduction to RL, and I wanted to give you a few quick examples just to kind of make it more concrete. So for instance, very important domain, the Flappy Bird domain. Hopefully some of you have played this game. I know it's a few years old now. But in Flappy Bird, here we go, we've got a bird that goes and tries to get past some pipes. So you can see at the beginning here, this bird is not very good. He keeps hitting the ground and goes back to the start state. So the transition function here is going to be controlled by the game. The action, if you ever played the game, you know it's just tapping the button, or excuse me, tapping the screen. When you tap the screen, you flap. So that's the only action you have. Do I tap or not tap? The reward could be the number of pipes that you passed by. So we saw that bird initially was just getting zeros. And then the state representation. Well, you could think, I could learn from pixels. But actually, it turns out, if you just know the distance from the bird to the bottom of the next pipe and the distance from the bird to the end of the next pipe, you can act optimally. So this is an example of where a human could come in and tell the agent exactly what to look at. And by focusing on just that, the agent can act optimally. Another more contemporary example is playing Atari. Even though Atari is decades old, again, you could hand code a representation. So for instance, talk about how far is the ball from my paddle in terms of X and Y position. Or with the advent of deep learning, now you could just reason over a pixel level representation. So this is one of the ways that deep learning has had a huge impact on reinforcement learning, where instead of having hand-coded features, hand-coded state representations, we can let our reinforcement learning agent learn a good representation. And this was a huge breakthrough by DeepMind. And I've been doing reinforcement learning for a long time. I kept trying to ignore deep learning, and then this came out, and myself and a lot of other people were like, wow, this could really be a game changer. The final example I'll use is now going to a real world example where DeepMind controlled a server farm. So in this case, they wanted to improve energy usage, and the equipment, what the equipment was doing, what the environment was, the weather, all of that interacts. So it's a complex system, and you need to adapt quickly. And all these data centers are different. So it's not like I can learn one policy for Edmonton and then deploy it in San Jose. That would be probably particularly bad. So instead, we might be able to use reinforcement learning. So again, it's a sequential decision process. I've got some state, so things like temperature, pump speeds, maybe something about the data load, and that's changing over time. And I can take actions. I can turn on and off different machines, for instance, and that will change things over time. The reward then could be something about the total energy used for what you're actually trying to do, which is compute, versus what you're using for cooling. And again, transition functions the real world. So this is one of my favorite examples of a physical system that's being influenced by reinforcement learning and optimized via reinforcement learning. Okay, so where does this leave us? RL can do things like autonomously maximize rewards. The programmer just specifies the goals. That can save a lot of time. You can get amazing performance, and you can handle changes to the environment. So at this point, you think, okay, RL is the solution to all of my problems. Well, there are a few weaknesses, and that keeps my job interesting as a RL researcher. So for instance, I mentioned that reward function. So how you defined the step cost in the grid world could change the optimal policy. There's a great example by OpenAI where they were having an agent learn to race a boat in a video game. And the agent learned to do a reward loop. So instead of finishing the level, it would just keep going around in circles, collecting points by hitting buoys. So your agent will go and maximize your reward, whether it's what you want to do, whether it's ethical, whether it's legal. So all of that should go into making you think carefully about how you want to define the reward. You can also need lots of compute. So if you are Google or DeepMind, maybe that's not a problem. For us mere mortals, that could be if you're in simulation. But if you're in the real world, if your decisions are costing you money, if your decisions are breaking robots, then you really need to think about how do I make things more efficient. Often the solutions are black box. It's harder to convince someone to use your AI solution if you can't tell them how it works. And like I mentioned before, that initial performance could be poor. So RL is not always immediately the easiest thing to apply, but now I'm going to transition to the second part of my talk. So if you had tuned out because you are already an RL expert, I'd ask you to join us back in again, because what I'd like to do is talk about how we can try to address some of those problems and how we can make RL even more useful for real-world applications right now. Great. There's another question about could we avoid overfitting in RL and improve the performance? So overfitting is a machine learning term, typically in supervised learning, where you train too much on some training data and then you don't generalize very well. However, Amir is right. This could have impacts in reinforcement learning too. So for instance, if I am training on a simulation and then want to deploy that on a real world robot, I want to I would like to have whatever I learn in simulation generalized and not overfit to a particular simulator. So there are techniques like sim to real, where you can do things to make it more likely that whatever you learn will better generalize to the real environment. So that's the strategies behind sim to real, for instance, are letting an agent learn over slightly different settings in the simulator. So for instance, having slightly different friction coefficients or slightly different gravity settings. There's also adversarial approaches to sim to real, where you have an adversary that's trying to poke the agent or poke the simulator. so that the agent performs worse, thus making the agent more robust to those small kinds of changes? Great question. Okay, so now transitioning to the most, to talking about me, of course. So I do a lot of stuff with multi-agent systems. Right now, I'm looking at humans and machine learning and thinking about how agents could teach other agents. So this could be transfer learning or a certain kind of teaching that I'll get into. This could be humans helping agents. So thinking about how do I help humans understand what an agent's doing so that they can help better. And also we'll talk a little bit about agents teaching humans. So I really want to emphasize that you can approach RL as a very much an artificial intelligence problem. I want my agent to learn on its own, go out there and just learn everything from scratch. I really want it to figure out all this stuff on its own because it's cheating if I let a human in. On the other hand, if you have a business process that you're trying to optimize, you want to cheat as much as you can. There is no reason to make the agent learn everything from scratch if there's knowledge you can imbue it with. So that's kind of what I've been pushing on. And when we're thinking about, well, so I've done some work in finance. Right now I'm doing some work in smart grid and drug discovery. I've done a little stuff in precision ag. But thinking about, we've got some humans, and maybe they're experts or not, but let's figure out how to use them. So remember I said there's lots of successes in games. That's true. One thing I didn't mention is OpenAI 5, the Dota champion, used 180 years of simulated gameplay every day. Let that sink in. 180 years. How did they do that? Well, because they had a huge server farm. They had the resources to be able to throw that kind of compute at it. That's incredible. And that is absolutely an exciting area of research to figure out what RL can do, what is possible given you've got all these resources. But if we're thinking about a small to medium-sized company that doesn't have $1 billion research budget, what can you do? How can you make things more sample efficient? How can you have agents learn faster? Well, and we could think about more, what are some of the challenges of deploying RL solutions? Because if you work in AI, you know that getting AI working in the lab can be quite different from getting AI working in a company, working in the real world. And reinforcement learning takes it a little bit further, can be even trickier. So in the past, I've talked about how you might try to approach RL from a business standpoint. I'm really interested in thinking about how to get RL into the hands of more companies. But today, I'm going to focus more on the more technical side, thinking about how we can use this external information to learn faster, because we don't want to spend 100 years worth of data per day. We want to be able to quickly get up and running, quickly getting good rewards without suffering all of those penalties associated with extra rewards, like compute, if you're in simulation, but in the real world, having those real world costs. So one thing you could think of is getting information from another agent. You could think of off-policy learning, which I'll go to in a couple of slides, and then think about getting help. So before I go all into this cheating, I do want to acknowledge there's a risk. So when you inject human knowledge into an AI system, you are biasing it. Well, any ML system is going to be biased, right? For instance, you could say, it's just a uniform prior. Sure, but that's still a prior. That's still a bias. So you need to be upfront about thinking about what kind of bias your algorithms have. And if we inject too much bias, we might be limiting our agent. So ideally, we want to bias the agent, but not prevent it from discovering solutions we didn't anticipate. Now, some of you might have seen Rich Sutton's post a few months ago about the bitter lesson, where it generated some discussion back and forth. One of his arguments was that when you try to shoehorn knowledge into agents, it's just a short-term fix. It's a kludge. And really, you should be relying on better algorithms, better compute to learn solutions on your own. And I don't believe that's always the right thing to do, because sometimes the existing tools you have aren't good enough to solve the problem you want if you're learning from scratch, and we need to figure out how to inject this bias. But you do need to recognize that it is a bias and it is a risk that you need to think about whether it's worth taking. So I think as long as we don't limit our performance, as long as whatever knowledge we're giving doesn't prevent you from finding the optimal solution eventually, I think it can be worth making that trade-off. What I've been working on for probably past 10 years or so is, instead of thinking of an agent in isolation, thinking about how that agent could learn from another agent, or learn from a human, or teach a human. So one of the first things you could think about is transfer learning, also now more often called policy distillation, having to do with deep neural networks. But here the idea is you've got one agent and you want to take its brain and stick it into another agent that's slightly different. Or maybe you want to take that agent and put it in a new task that's slightly different. How do you reuse that information? So when you have access to agents' brains, when you have access to their parameters and hyperparameters, this is absolutely an appropriate choice. And it often depends on the type of RL algorithm, sometimes the function approximation you're using, the setting. Another thing you could think about is designing a curriculum. So for instance, if I have this difficult task I want to learn, it can be faster to train on a sequence of simpler tasks. And it can be faster to train on that entire sequence using transfer learning in between than it is to directly train on the final task. It's not too surprising. I mean, that's how humans learn. We don't directly start. My daughter's in kindergarten. I'm not teaching her calculus. She's got a few steps to go first. So curriculum learning is a very interesting open challenge. But for this talk, let me assume I do not have access to a trained agent's brain. And certainly, if I have a human, I do not have access to their Q values or their policy. So what could I do instead? One approach is off-policy learning, also called batch reinforcement learning, where you just have a data set. So think about if I want to work with healthcare and try to figure out a good schedule for giving someone drugs. Turns out hospitals probably aren't going to let you explore with their patients and try different drugs, but you could look at a data set where people have given past patients drugs and looked at their outcome. And based on this data set, you might be able to learn something. Now, the important thing here is this data set could come from humans, as in this case, or it could come from an RL agent, or even a hand-coded program. So this is usually something where where we're trying to improve something. So you've got some existing process that you think could do better because you want to handle non-stationarity, you want to achieve better performance, so you want to put RL on top of it. And there are questions about how good does this set of data need to be? How big should it be? How stochastic should it be? Because, for instance, if every doctor treated every patient in exactly the same way, you're probably not going to be able to learn a whole lot from that. So one of the questions you can ask is try to understand what a policy would be if you deployed it. So I've got an agent that learned some policy pi, and I want to think, okay, now if I let it take over the dosing of people in hospitals, what would that performance be? And I could put some kind of bound on it. So this way you could say, okay, I am very sure that if we use drug A instead of drug B, things will be better. You could also do policy improvement. So say, I'm going to look at all this data and figure out the best sequence of drugs that I could provide. So you can have this policy improvement. And it turns out you can even change the behavior policy to get better data. So for instance, going back to this setting, if I could convince some doctors in the hospital to try to use drug B instead of drug A, like you might expect, I can better evaluate a different policy and know whether deploying that policy makes sense. So there's a lot of great work that's going on in this off-policy setting, and I think it's going to be very important for getting RL into the real world where where exploration is dangerous. One of the things my student and I, Hagar and I, are looking at is thinking about when we should switch from a policy. So let's think about a stock trading example, right? You're paying someone to trade stocks for you, and over time you can look at how they're trading stocks and say, okay, I think I've got this. I think I understand the method. I'm going to stop paying you to trade stocks, and I'm going to take over myself. So at some point, it may be you've learned enough, you're confident enough that you are going to stop paying them, and you're just going to do it yourself. And so that's one open question. When do you want to make that trade-off? But we could also think about, what if we could influence the behavior? So what if you could call up your stockbroker and say, buy me 100 shares of IBM right now. And then you do that to selectively collect data that helps you learn a better policy. Of course, your broker might say, no, that's stupid. Well, okay, your broker probably isn't going to do that. But what if you had a self-driving car and your off-policy learner really wants to see what happens when you crash into a tree? Maybe you shouldn't demonstrate that. In which case you could learn something about, wow, what I just thought I wanted to collect more data about was a really bad idea. So maybe that's something I want to avoid. And this comes back to the value of information. Thinking about, if I'm trying to get more data, where do I want to ask for that data? So that was off policy or batch. Now let's think about, could I get help? So again, this could be from another agent, a person, a program, but they're likely suboptimal. And we don't want to just look at nerds. So for instance, one of my friends, Sonia Chernova, ran a study with her student Ben and some others a few years ago, where they looked at 3 learning from demonstration methods. So these were methods where people taught robots to do different things. Pretty cool. But they took those methods, and instead of getting human demonstrations from roboticists, they got demonstrations from normal people, and they got different results. And that's not completely surprising. But we want to develop methods that don't require expertise in machine learning. Maybe we don't even want necessarily expertise in a task. So let's see, how could I provide help? Well, you could think of demonstrations, which I just mentioned. So teleoperating a robot, playing the game for it. You could give action advice. Hey, robot, go right. You could give feedback. Good robot, bad robot. You could give preferences. You could give natural language. You could do all of these different things. And it's an open question now where one kind of advice would be better than another and where it would be appropriate. So for instance, I might be able to give good demonstrations on Mario, but I'm not going to give good demonstrations on controlling a helicopter. So maybe if a helicopter is trying to learn, I could give it feedback. You just crashed. That was bad. Right. And we've got another question. Should we inject knowledge that we know for sure as much as possible? So, for instance, Wally could have moved towards the wall if just tell Wally, dude, don't move towards the wall. And I think that's right. And you could either think of this as advice, saying, hey, Wally, it's a bad idea to move towards the wall. Or you could think of it as a demand. You could hard code Wally so that he will never move towards a wall. And if you did that in some of those reward settings, you wouldn't be able to learn the optimal policy. So that's a great example of you want to provide bias because you can help the agent learn fast, but in some cases, you want to leave open the possibility that that advice is not optimal in all settings. So now I want to give you a particular example of how you could learn with demonstrations. So for instance, you could have a human sit down at a keyboard and in a state, take a certain action. So the human can sit at the keyboard and play this game. The agents in a state takes an action. Agents in a state takes an action. And this is data. And we could take this data and just use some kind of classifier over it. So in this particular case, human agent transfer, or HAT, what we did is used a decision list learning method to go and summarize this policy in terms of a classifier. So this classifier could say, well, in this state, here's what I think the human would do. In reinforcement learning, you often trade off exploration with exploitation. In HAT, what you do is say, I'm going to execute the suggested action with some probability. So for instance, initially there could be a high probability of executing the action I think the human would take. And then over time, you reduce that probability so that the agent can exploit its own knowledge. So again, initially you force it to do what you think the human would do. Then over time, you ease up on that and let it decide on itself, on its own. So an example of this is in the domain of keep away, where we've got, in this case, we've got 3 keepers trying to maintain possession of a ball, 2 takers that are trying to kick it out of bounds. And the human can sit down and demonstrate this game. So play the game. Unfortunately, my recording isn't working, but it moves at a decent clip. So the human has to decide for the keeper with the ball, do I hold on to it or do I pass? And if I pass, who do I want to move? Who do I want to pass it to? Try to pass it to. So we can get these demonstrations. We summarize these demonstrations in terms of a supervised learning classifier. And then I let my agent learn being biased by this classifier. In reinforcement learning, here's typically you see learning curves. So along the x-axis, you have simulator training time. Y-axis is performance, episode duration. And you can think of different ways of measuring this. So for instance, the jump start. Well, the initial performance is pretty similar between just learning from scratch or using HAT, which is labeled PPR here, because that's the particular version that we use. But we could also think about the final performance or the total reward, so the area under the curve. You could also think about time to threshold. So let's say we really cared about our keep away players getting to a performance of 14, maintaining the ball for an average of 14 seconds. And then you could say, well, how long does it take with these between these two methods? Well, it looks like it goes from like 14 hours to around 8 hours. So not quite 50% savings. That's kind of cool. But then, if you step back and kind of squint at these lines, Matt, okay, I see 2 lines, but they're really pretty similar. Is this actually interesting? And the reason I would argue this is interesting is we're getting this kind of improvement, about half of the training time, with only 3 minutes of human demonstrations. So this is one of the key points, is that the human demonstrator was not optimal. In fact, we could make the human, by speeding up the simulation, we could make the human demonstrator worse. But even 3 minutes of suboptimal human play gives you this huge improvement because RL agents are acting randomly initially. And you see that even this bias doesn't make a huge initial difference, but it helps you learn faster. And that's what we've seen again and again, that this kind of human bias helps you learn faster, even with very small amounts of data. So this was HAT. Pro tip, when you make your algorithms in your paper, don't call it my algorithm or our algorithm, come up with a fun name. So we took HAT, and then we decided to improve upon it by making confidence HAT, or chat. So we took chat, was saying we're going to do the same thing, but now I'm also going to have a confidence. So I learn my classifier, and then I also estimate how sure am I that the human is going to take this action. And we could use different methods. So we could use a neural network or a decision tree or a Gaussian model. So there's some implementation details, but the only algorithmic change is I'm only going to listen to my demonstration if I'm fairly confident in this is what a human would do. So with just this slight change, saying I'm going to be biased towards listening to what I think the human would do when I'm more sure in that estimate, we're able to get improvements. So I won't go into the details here, but this is different domain Mario, and using this extra confidence, we are able to get better performance. So how to best use demonstrations, how to let those demonstrations bias you, but not prevent you from learning good policies, and how to use demonstrations that could be of different qualities is exciting open research. But we do have a number of examples where it's working. And if you're going to deploy an RL agent in a situation that you care about, why not use this kind of bias? So here's an example of demonstration. Now let's think about getting help in general. So think about action advice. So for instance, you could say, well, a teacher, a human, another agent could be looking at a student agent and say, oh, dude, you're about to make a mistake. Here, let me tell you. So for instance, I see you driving towards that tree. Please don't drive into the tree. Or the student. Well, the student knows exactly what's in its head, and maybe the student knows what it doesn't know. That would be cool. Then the student could ask for help. Or there's this nice work by Ofer Amir when she was an intern at Microsoft Research, where you could combine both. The student could ask for help. The teacher could provide help. So it's a cool way of thinking about how do I, if I've got a knowledgeable agent, how do I get that agent's occasional help? One of the things we're looking at is whether explainability could help. So for instance, if I have an explainable RL agent, maybe those explanations could help a user decide which agent they prefer, or make you better predict how an agent would act. Most relevant here is, could explanations let a user give better feedback to an agent? So for instance, in Pac-Man, you could have an agent that is going down a hallway, and maybe it's going down a hallway for the wrong reason. If you knew something about why the agent made a decision, hopefully you could provide better feedback to that agent. So we can think about, well, okay, where should one type of help be preferred? Who should initiate it? We could also say, specifically, what happens when the help is not unlimited? So there could be a total budget. So we did some work saying, well, you can query the agent the teacher a certain number of times, because maybe it's a person and they're going to get bored real quick, or maybe it's another algorithm, and this budget is a way of making sure that you don't rely on it as a crutch. So one of our recent works was using an ensemble method. So we have lots of different estimates for Q values, and this agent, this student, asks for help when the Q values disagree. So this simple but effective way was a proxy for measuring student uncertainty, and this enabled us, let us get very significant improvements. But you could also think, well, what if there's not a total budget? What if there's a cost? And there's actually some cool work out of Waterloo where Colin and Edith were looking at exactly this. And you could think of the cost being, you are paying a crowdsourcing person, so you are paying someone on Mechanical Turk, and you might need to think about, okay, how do I trade off agent performance with paying someone? How do I think about those two possibly different things? And one of the approaches we're taking right now, this is work by Amir, is thinking about value of information in a multi-arm bandit setting. So let's say there's a teacher, an oracle, and I could either pull the arm on that multi-arm bandit with the highest expected payoff, or I could pay my oracle some amount, and it could tell me the payoff of a given arm. So depending if that cost was free, I would always ask for help. If that cost was prohibitive, I would never. And there's probably something in between that's pretty interesting. And then going back to what I mentioned before, what if I'm trying to learn to play a video game and I'm paying a person? How do I compare those apples and oranges? Okay, so again, this is thinking about value of information. So let's take a couple of questions. If you're using a suboptimal human, aren't you always limited by their suboptimality? And no, because in all of these methods, we want to get this advice from a human. It's a bias that we can learn to overcome. As long as these aren't 100% fixed rules that we must always obey, then we are still able to use this as a bias, which lets us eventually outperform the human. And that's what we've seen in many cases where a suboptimal human lets an agent reach a really high performing policy faster than not using it. And the RL agent is able to outperform the human. And how do you know that these demonstrations don't stop you from learning the most optimal policy? That's a great question. And so, for instance, with HAT, you turn that probability down over time. So eventually you can't rely on the demonstration. And we do actually we've got one theoretical paper on using action advice where we can prove that even if the advice is not good, as long as it's limited, you will be able to learn the optimal policy. Great questions. Okay, so now the final thing, we could think about, well, what if there are multiple teachers? So you could have one teacher that's really good at collecting coins in Mario. You could have another teacher that's really good at doing speed runs in Mario. How do you figure out who to ask for when? Or how do you figure out how to combine their advice? What if one of them is more expensive? Do I want to ask one person a lot of advice that's okay? Or do I want to pay for a little bit of advice that's really good? You could also have multiple students. So thinking about you're coaching a soccer game, you could either yell at the team, push forward, you could yell at your forwards, go towards the goal, or you could yell at a particular player, Matt, stop lollygagging, get up there. So you could think about, who do I want to give advice to? Maybe I can't give advice to everyone at once. And one of the things that comes up with this is even if teaching doesn't have an explicit cost, if you're helping one agent, you might not be helping someone else. Or if you're giving more or less specific feedback, how do you figure out what level of specificity? And you could do other things, make things more complicated. So thinking about, instead of a coach, think of the captain. The captain of the team is on the field and it can only talk to people close to him. Or what if the teacher is learning too? I've been assuming that the teacher is fixed and the students are learning, but what if the teacher is learning? So there's lots of interesting open questions here. That's one of the goals of this talk, is to not only convey that using external information is important and useful, but also there's lots of cool research that's going on here. Okay, and the final thing I'll mention is we could also think about this final direction where we have an agent that could teach a human. So this could be related to intelligent tutoring systems. And you could think of trying to teach a sequential decision process. So for instance, if you played Portal, Portal is a first-person shooter game, well, kind of shooter, but it's got this really nice tutorial sequence where it builds up these different tasks over time, a curriculum, and teaches a person the ins and outs of the game. And Levy and I had this project scoped out where we're looking at a particular game that he developed, and we're thinking about how could we use agent advice to help a human learn more quickly. So thinking about what's the difference between the teacher saying, hey, Matt, you should go right, versus me saying, help, I'm confused. Is there a difference between saying you should go up versus here's the entire trajectory to solve this game? And we're also thinking about productive failure. So instead of just giving as much advice as you want, limiting that. So for instance, when I was learning how to play chess, I was playing on the computer and just asked for hints on every move. That didn't help me learn. That just helped me learn how to ask for hints. So I'm bringing this up in particular because we had this whole project outlined. It was a nice master's thesis, but then the student decided they would rather focus on something else because this was starting to feel too much like education for them. So this is one example of a project that is ready to go if we could find the right interested student. Okay, so I tried to give you kind of some insight into the kind of methods that are out there. I went into a little bit of depth, but it was pretty superficial. I went into to talk about HAT, just to give you a sense of what's possible. But the main goal was trying to get you think about what kinds of external advice are out there, and to get you thinking about, if I've got an RL problem, what external biases could I use? And is it worth the risk that it may be harder in the long term to learn that optimal policy? Because if I provide poor biases, you absolutely can hurt learning performance. Well, so if you found this interesting, I am teaching a graduate course in the fall semester at U of A, which is completely online, and all the materials are available. So if you would like to learn more, you're welcome to go to this website, or you can search for interactive machine learning at U Alberta, and all of the classes are up on YouTube, as well as all the materials. And in the coming month or two, we are planning on releasing HippoGym, so the human input parsing platform for OpenAI Gym. And this platform will let you do these kind of human subject experiments, letting RL agents interact over the internet with people. So you can get people to play Pac-Man for you. You can get people to give you feedback. You can have people click on the screen saying, hey, that was a mistake. So we're going to release this open source, and we're hoping that this can help speed up this kind of human reinforcement learning research. Oh, side note, we thought we were being really clever with this cool name, HippoGym. Turns out HippoGym at Gmail was already taken. There is, in fact, a HippoGym. I believe it's in Europe. Go figure. So if you're interested in learning more about reinforcement learning, there's great classes at Waterloo taught by Pascal and Mark. There's also a bunch of online resources. So my favorite are the Coursera class. The Udacity class is also good and free. Also, these resources will be on the final slide if you want to take a screenshot then. Also, this content will be online. There's the book about RL, Sutton and Bartow. If you have a more algorithmic bent, if you are more looking for a very condensed, mathematically savvy introduction, I recommend Shaba's book. Or if you're not so much interested in RL in general, but really want to learn more about deep RL, then I could recommend the classes on YouTube from UCL and DeepMind, or OpenAI's Spinning Up set of tutorials. Let's see. Oops, I didn't scroll down, and now I see there are more questions. So actually, let me. Oh, thanks for dropping the classes in the chat, Mark.
Yep, no worries.
So let me just wrap up, and then I'll knock off these other questions. So my hope is that as people learn more about RL, they'll understand that it is a mature technology and figure out where and when it can apply. So the thesis in this was, yes, external information can and should be used, as long as hopefully it doesn't bias you too much. There's lots of kinds of information we could be using. And thinking about all of this is kind of related in a lot of ways to the value of information, figuring out what I want to ask when. So I am always open to suggestions. If you know about something that I missed, please do let me know. If there's some magic bullet I don't know about, please let me know. I want to know now instead of later. Always open to collaborations if this is interesting to you. And with that, I'll just leave this final page up. But let me answer a few of these questions before we open it up in general again. Let's see. Do you know that these demonstrations do not? Oh, sorry, I already answered that.
I think Rash's one on continuous DDBG, GD3 hadn't been answered. That was like really
good.
Early.
Yeah, that was the early one. So let's see. So how can we make continuous space algorithms robust to uncertainties? Right. So Rash, so if you are interested in using deep RL, normally the places to start are things like PPO or TD3 or SAC, soft actor critic, depending on whether you have a discrete or continuous action set. All of those actions will work over continuous space. Now, uncertainties, it really depends on what you mean. So if you have uncertainties in how you should act, if the agent has uncertainties, you can absolutely use that. So uncertainties can help bias your exploration. It can help bias your actions. Maybe you want to take the slightly worse action that you're very sure about instead of the possibly better action that you're a little bit riskier. You can also think about explicitly reducing those uncertainties through external information or just through interacting with the environment. So Arash, if that did not answer your question, please ask it again in the chat and I'll try to readdress it. So I see that Mark dropped some courses in the link, so that's awesome. There's also links about Waterloo AI. Then human demonstration and human feedback seem like two different terms. That's right. So that's a great point. So when I say demonstration, I'm thinking of teleoperation, or this could be kinematic manipulation. So taking a physical robot arm and moving it around. That's demonstrating the state action sequence. Whereas when I say feedback, that could be more like, that was good, that was bad. So, and you can learn from just that. You know, humans can teach dogs to do amazing things, bomb detection, seeing eye dogs. We can teach dogs how to do cool stuff. We can teach computers. We can teach robots through that same kind of good robot, bad robot. And it could be in a setting where there's no reward. You're not in an MDP. There's not a reward provided by the environment. The reward is only coming from a person. Or you could be in a setting where there is an environmental reward, and this human feedback is just on top of that. So that was a great question, because I think of demonstration and feedback as two different terms, but you're absolutely right that there are different things you could think about. Awesome. So I am now at 61 minutes, so this would be a great time for me to take a dramatic drink of water and ask for additional questions.
Great. Well, we'll have a applause quietly, even though we can't hear everyone. We've got to find a way to pipe everyone's sound in, but thank you so much for that broad, high-level overview of RL, as well as deep dive into a couple of the theories you do. It's great. I think the video is going to be useful for people, and we had really good discussion. But definitely, we have extra time. So if you have any other questions on any different parts of that, feel free to throw them in. Oh, here comes one. Great. So the perfect humans, is that useful? That's a question.
Okay, so is there value of learning in domains where you have perfect human expertise, like soccer? I was with you right up to the very end. So some of you may have heard of RoboCup. So RoboCup is this long-running challenge in simulation and physical robots, where the goal, I believe, is by 2050 to field a team of robots that can outperform the human world champions. So I'm not sure that, thank you, I'm not sure that humans are perfect there, but let's say they were. Let's say humans are perfect. Then in that case, what you would want to do is learn to mimic the humans. Because you're going to assume, because if the humans could always control the task, then what's the point of using automation at all? So then the question is, how well can I mimic the humans? If I had an infinite amount of data, I could replicate the humans perfectly. But if I don't have an infinite amount of data, then there will be places where I don't have a human response memorized, and I have to generalize from my previous experience. So that's an example where you still would need some kind of learning, because you would want to iteratively or over time both learn to mimic the human, but also fill in the gaps because you don't have an infinite amount of data. Could you teach an agent to do more exploration or exploitation? Interesting. Yeah, so there's lots of different ways of guiding exploration. So one thing you could do is instill the agent with a sense of curiosity. So for instance, you could tell the agent, you don't know anything about light switches. You should be very interested when a light turns on and off. And then the agent, once it runs into a light switch, starts messing around with it, say, hey, this is cool. And then once it figures out the light switch, it stops messing around with it because it's no longer novel. So that's one way of directing exploration. Another thing you could do is, let's say you've learned a bunch and now you're exploiting. You are in a grid world and you're just going to that treasure chest. You could have a person saying, dude, you're missing the real goal. Yes, you found a +10, but I can see the +100. stop messing around with the plus 10, do more exploration. Or you could say, okay, I'm getting to work in 25 minutes every day. Maybe I could get there 24 and a half minutes, but it's not worth risking a 30 or 35-minute commute. Just stick with this one. So that's a great point, that you could absolutely have the human help control this exploration or exploitation. Great. Arash went back and corrected that he meant the simulation model uncertainty and disturbances in robotics control problems. Yeah, so one thing I didn't get into is the idea of model learning methods, or also called model-based methods, where I estimate the transition function. So I estimate how, when I take an action, here's the next state I think I'm going to get. And if you are learning a model of the world, if you understand your uncertainty, you can absolutely do clever things like changing your exploration or active learning to learn a better model so that you can exploit it and use planning. And the disturbances in robotic control problems relate to this, right? Because if you have a model that you've learned, no models are perfect. Some models are useful. So if you understand where your model is better or worse, then you can absolutely exploit that. Okay, and then we've got a question about I talked about final performance versus speed of learning. And Alex is pointing out that there's research in continuous control from images that started looking at performance after 100K environmental steps versus 500K environmental steps. And that's a great point. So when I'm thinking about a learning curve, there's lots of different things I could care about, and it really depends on the setting. So if you are interested in the performance after 100,000 and 500,000 interactions with the environment, that is absolutely something you could benchmark and compare with and try to optimize. The problem is, in some Atari environments, you might care about 50K, not 100K, or you might care about 0K. How am I performing at the beginning? So it's absolutely a great idea to think about, well, what do I want to maximize in this particular setting, and how do I measure it? Because if I do not have metrics, then I don't know what I'm doing. I'm just, this curve looks higher than the other one.
Yeah, that's a great question. Is the connection between this and control and the right ways to kind of trade that off and use what we do know is really something that's still very open, right?
Yeah, absolutely. Actually, Mark, do you want to say anything about your reinforcement learning research? Do you ever use external information, or are you more of the pure variety where I just want the agent to learn on its own?
Yeah, we've been usually using things with where the reward function and the provides the feedback, because we're trying to optimize towards the behavior of some type of system, or we even sometimes use reinforcement learning almost for regression type problems where we want to recreate a system, right? So we do like, you can try to use, essentially learn an agent-based model of fire spread by saying, can you recreate the fire you saw? Which is kind of a reverse way of doing this. But another thing that we're kind of working on now is looking at how to integrate experts kind of knowledge in when you have multiple experts into your system, and what's the right way to do that mathematically, but also efficiently. So there's important stuff on all those sides.
That's awesome. Yeah, because if you get a bunch of experts, you could do some kind of preference elicitation to figure out what the right thing is, and depending on how you change that reward. So, for instance, if you use potential-based shaping rewards, that's one way of tweaking a reward function where you will not change the optimal policy. But in practice, you often add non-potential based changes to the reward function because it just works better, even if you then risk getting a different optimal solution.
Yeah, well, again, it gets back to what you're saying, like RL, you're focusing on essentially a practical concern because you're trying to do well at this problem, right? Is it optimal? Is it the correct way to solve it in terms of the way you can interpret it? Maybe not, but if it does better at that domain and wins the video game or runs your factory, it's worth it, right? But you also got to worry about whether your biases, what you assume has to be the solution, are going to wreck it. And you actually have a question about reward shaping, so it's perfect.
Oh, awesome. Good timing. So Sola asks, are there any good advice in reward shaping for complex RL problems, like high-dimensional robotic control? Is domain knowledge a must? Great question. So we didn't really talk much about reward shaping, but you can think of it as saying, I've got this MDP reward coming in, and then I could have someone else adding some extra rewards. So for instance, if I'm doing a maze task, I get 0 at every state except a +1 at the goal. You could add a shaping reward saying, I'm going to give you a slight bonus when you move towards the goal, and I'm going to give you a slight penalty when you move away. That bias should help you learn a lot faster. So in that case, I don't necessarily need to be a maze expert. Or think about it this way. If I am trying to get a robot to learn to walk, and I give it a +1 when it walks and a 0 when it doesn't, I could have a person say, hey, you should give a shaping reward where when you don't fall over, you get a +1. That's not a potential-based shaping reward, but it is a reward that might help you get to a walking policy faster. So in that case, you could probably have a non-expert give that kind of shaping reward, or an expert might be able to give you a better one. But thinking about that trait, so we did some work a few years ago where we looked at students who had taken, I want to say 2 or 3 weeks of an RL class. So we took these students, and then they had some programming ability. So we had them program a representation for learning in different tasks. So they were not RL experts, but they were able to provide some advice. In this case, it was a programmatic form. So you could absolutely have people either give this kind of high-level shaping, or you could have them actually write down a function. So if they wanted to write down some complicated function because of their domain expertise, that could absolutely help.
And I was just going to say, related to that with the robot, you could think that in that case, there might be very specific expert space for reward, because you could say, well, the hand is near the location you want, but that may not be very near because the joint angles don't get you from A to B very easily. So you want the angles to be close in some space, right? And we're doing other work, actually, I hadn't mentioned this one, but physics, and we're definitely wanting to do that because we're trying to relearn certain ways that chemists kind of can turn one material into another. And that's a complex process. Nice. And you have really clear data because you got experiments in and out. It's perfect for just saying, oh, we'll learn it for deep network. But the thing you're learning is chemistry, right? Which is pretty complicated, right? And so why not use the human knowledge that you can, but then you get it to find the better process for doing that. And so Alex has a follow-up on her with some more detail on what she was giving as background. So you have to read that a bit. More about intrinsic motivation.
Okay, so Alex is talking about intrinsic motivation and how in her research she's using, sorry, I'm not sure if it's her or he, in their research, they're using goal-based reinforcement learning and try to reach a goal as fast as possible. Then you want to get a good sample of goals, and then that can be transferred directly to a downstream task. Yeah, so thinking that, and it brings up an interesting point, because in many cases your goal is not necessarily to get your agent to learn this one task. So if we say I want to learn Pong in Atari, okay, yes,
they don't know what Pong is.
They don't know what Pong is.
Well, I always try to, when I go back to these games, like, here's what Pong is, just in case.
So in Pong, there are 2 paddles. It's supposed to be kind of like tennis, where you bounce the ball back and forth, and you don't want the ball to go past you. And you could try to learn Pong, but you're right, you probably want to generalize to other problems. So for instance, if you can learn to play Pong, but then when you change the paddle size slightly, if your agent just breaks, that's probably not as interesting. So if you can use intrinsic motivation and curiosity to help you better explore a space, so that when there's a slight change to the problem, or when you take it out of simulation and deploy in the real world, or if you take it out of this task and bring it to a different task, hopefully you can better generalize there. And then the follow-up was sparse binary reward for continuous control in robotics can perform better than shaped rewards. for instance, using hindsight experience replay, her, which is also used in goal conditioned RL. Yeah, so I don't know about this particular. I mean, I'm familiar with her. I can't remember showing that a good shaping reward doesn't do as well, but that is interesting. I could imagine cases where that could be true.
Right. So maybe we'll just wrap up. I don't know if there's any others. I think just one last thing about handing off, because you talked about it a bit, like how do you know your RL agent is good enough to trust it to take over driving your car, which everybody asks. It just seems like it's hard. It has to be done on performance and expression, but do you have any ideas about that?
Yeah, well, I think that's actually a very general question, because if you are talking about taking over, then it's not just a matter of, well, convince me the performance is better with 95% confidence intervals, and okay, but that would convince a nerd like me. But if your system is explainable, if your system can help the user build trust and understanding, those might even be more important. If you can have your salespeople explain to a customer how the car acts, the customer may well prefer that over another model that a different dealership with a salesperson just says, it's a deep neural network, don't worry about it. Mm-hmm. But I think that's a critical point, that as we go and develop solutions for companies, when you go to your boss, when you go to the CTO and say, please deploy my solution, how are you going to convince them? How are you going to convince them that your simulator is accurate, that your performance is good, that your performance will generalize? All of that is really interesting things that we as a community need to start grappling with, so that we can take this awesome tool out of video games and into the real world.
Great. So I think that's a great place to wrap up and end on a hopeful note, and for future work. Lots of research to do, as you're saying, and it's a growing community trying to do it. So if you're interested, talk to us. And I also posted the link on there just for the Institute in general. If you're within the Waterloo community especially, you can join this team environment, and we have more news about events and stuff going around on campus and nearby. So please request to join, and I'll add you. And we can involve and link back to speakers, previous speakers as well going forward. But thank you so much for the talk and the discussion, Matt.
Well, thank you for inviting me. This was really fun. And I look forward to interacting more with you, but also the Waterloo AI community.
For sure. Great. Okay, so we'll leave it there and see you all next time. We have another talk, hopefully on November 3rd. We'll be sending you some more information about that. See you then, and stay safe.
Thanks.